Hello, my friend. Today we're gonna solve together an exercise coming from the book. Indeed, we are gonna solve the exercise 2.1, namely the first one of chapter 2, which I decided to be the first chapter because, strangely enough, the first chapter of the book is much more complicated than all the other ones. The book is made in this fashion because it wasn't thought for average people, right, to learn how to code. Back in the days, the book was thought for professionals, right, because there were not so many computers everywhere like today. Everyone nowadays has a supercomputer in its pocket, and coding should be taught to everyone, in my opinion. So today's exercise is this one. We have to write a program to determine the ranges of char, short, int, and long variables, both signed and unsigned, by printing the appropriate values from standard headers. You will see we are going to use the headers file float.h and limits.h, in which there are all the symbolic constants representing the ranges of the values. You will see. The difficult part is that we have to compute ourselves the ranges. So we have to really understand what is going on underneath those. So to be everyone on the same page, let's just make a quick recap. So you perfectly know that this is the RAM, and inside the RAM there is our process, our program that is running. Here lives our main, and of course all the variables which are inside the main function. When I say main, I mean the program in all its glory, not only the main function, of course. This view of the chip doesn't tell us anything about how to exploit the memory, so we programmers have this view of the RAM, right? We see the RAM as a series of slots. These slots are bytes. Every byte has its own address, and every byte is composed of 8 bits. A byte is just a little byte, indeed, of information, and 4 bits are just a nibble. So you can perfectly well visualize a byte as 8 light bulbs with a specific address in your memory, in your RAM. Inside this RAM, you can stock stuff. Basically, this stuff is what we call values, data types. We have integers and we have real values. Char, short, int, and long are all integers. The difference between these values is the size. A char is 1 byte, a long is typically 8 bytes. So the difference between these data types is the amount of information they can stock. But inside these slots, there can be only numbers, okay, in the integer form. We have also real values coming in the form of floats and doubles. Float are 4 bytes, double are 8 bytes. Of course, when I say char, short, int, and long, this short and this long are qualifiers. Indeed, the short is a short int and a long is a long int, okay? So when you say short, you're simply telling to the compiler, hey dude, I just want 2 bytes, I don't really need 4 bytes. When I say long, I'm saying, hey, maybe I need more space for my variable, which is an integer. Okay, that's all there is. So I can really surgically decide how much space I want in memory, right, with this short and long. But I can also decide if the value has to be signed or unsigned. The sign of a specific value is defined by the first bit, by the most significant bit. By default, all the values are signed. If I want to make the value not signed, I just use the unsigned qualifier. So as you can see here, let's pretend I have a char that I call C. A char is 1 byte, as you just saw, and this is an integer. Indeed, a char is just an integer of 1 byte. When a char is signed, what does it mean at the end of the day? What is the result of this? Well, it means that you can encode positive and negative values. So you have to split into the representation. So we have 2 to the 7 possibilities, 2 to the 7 patterns, so 128 patterns for the positive values, as well 128 patterns for negatives. So I can represent from 0 to 127 for positives, and from minus 128 to minus 1. I represent one more with negatives because I don't have to represent the 0 2 times, right? Logical. So the maximum value I can get with a char is 127, okay? The maximum positive value of a signed char. On the contrary, if I add an unsigned char, what does it mean? Well, it means that I can use all the 8 bits to represent a value. So here I have 256 patterns. It means that I can represent a value of 255 this time. Essentially, I doubled the amount that I can represent. So let's make an example with an integer. Here I have a signed int. I repeat to you that I don't have to write signed qualifier because it is done by default. If I want, I can also write signed, but it is not necessary. And in real code, you will never see that. So I have int n 2 billion and something. This is int max. So as you can see from the image, I have all the bits which are turned on, but the sign bit, okay, which is turned off, of course. So this value is 2 to the 31 minus 1 because I have to represent the 0. You understand this? Now, if I make this value unsigned, I have 1 bit more, and 1 bit more means that I doubled the value. So I can represent 4 billion and something. This bit value, which is 2 to the 32 minus 1 still. Every time I double the value that I can represent. Of course, the bigger the number, the more remarkable is the double, because this is exponential, you understand, right, at this point. Okay, so we are here, we are on the same page. Depending on the qualifier, depending on the data type you decide, you can finally tune the amount of space you want and the value that you can represent. So this gives you really this big power to surgically control your RAM. So first of all, we are gonna write the values, the ranges that we can represent with these data types that we have at our disposal, thanks to the library limits.h, and of course float.h, in which we have the ranges for floating point numbers. So limits.h and float.h are header file. They contain stuff. Indeed, they contain symbolic constants, namely some defines, right? There are some definition of this constant. As you can see here, we have char bit, char min, char max, or short min, short max, all these important symbolic constants. The most used one in real code is, of course, int min and int max, because integers are the most used data types. So header files are important for portability. You can write code that is portable across different systems and platforms. The code is overall much more readable when you have these symbolic constants, big more readable. The code is also maintainable, much more maintainable, because it's trivial to understand what is going on once you write code that is very, very readable. So to write code that is readable is really, really important. So as usual, we open our terminal and we write vim ranges.c. First of all, we're going to do the integers and then the floats. So here I'm going to include, of course, standard input output, like always, because I want to use the printf to see the results. And this time we're going to also include what? The limits.h file. This is a file which is in your system. You can watch online, for example, limits.h. You go here, tutorials point, and you will see that you have basically everything there is written. So long story short, we are gonna do that now. You see, basically I can copy paste now. So I'm gonna just do the first one just to get the gist of it. So int main, our main function, and we do for char, very simply, we do printf, the max value of a signed char is %d, new line, and here we put char max. Very simply, right? We can basically already run this to understand what is going on. Run ranges. And this is, of course, the max value of a signed chart, which is 127. So long story short, this is all the program in all its glory. As you can see, I have the char, and I print for every specific data type is specific symbolic constant, right? Signed char min, signed char max, and unsigned, and so forth. For all these data type, this is super trivial. So we just run it and we are going to see the result. As you can see, I have the values from char, the values from short, which are correct, the values from the integer, and so forth. The long has a very big value, especially the unsigned. For the real values, this time we have to use this header file, which is float.h. Float.h contains these symbolic constants, right, which contain the maximum, minimum values of these real values. Let's watch just very briefly the float, okay, so we can, given that they are all the same. So the minimum positive value here of a float is represented by float min, and here this fancy %e stands for the scientific notation, right? This stands for exponent in bigger case, uppercase. Here we have the minimum positive value, the real number. As you can see, I need 100 elements. I just put myself 100 to see a lot of numbers, even though less are fine. But it is a 0.00. There are many zeros here because it's the minimum value represented by a float. Here as well, I have a maximum value in scientific notation, as you can see from this e, and the symbolic constant is float max. as well here the same, but I want to see the value. Here I have something peculiar, which is float true min. I will explain you later about this. It is a very specific in the way real numbers are stocked in memory. And here we have a symbolic constant, which is specific to real numbers because it is going to tell us the precision, how much precision we can expect from this specific data type. Okay, let's try to launch this and let's watch the output. So run limits.float. Here it comes. So this is for floats. We have the minimum positive value, which is in scientific notation. So we have this, which is the significant part of the value, as known as mantissa, elevated to minus 38. As you can see here, we have the real deal, which is a number with 38 zeros just before. And then we have, of course, the significant part, which is this one, which is equal to this, okay? So the scientific notation gives us a really neat way to represent values without having all this madness, okay? So as you can see here, we have the maximum value in scientific notation, which is pretty big, is this number here, right? Pretty long. Then here we have something which is called positive subnormal value. Here, again, we have to understand really well how these floating point numbers are stocked in memory. We will see later. Then we have the precision value, which is of 6 for floats, okay? So I have a precision of 6 figures. Here we have double. Double is very, very big. As you can see, the maximum value is this big boy here. Look how big it is. Maximum value representable by a double, as well as the minimum value is small. Essentially, I cannot see it because it's too small. We have to increment a little bit. So we're gonna put after the point just 400 values, okay, 400. Okay, we save, go out, and then we launch again. As you can see, pretty tremendously little, no ones. And also we have subnormal values, which are as well very, very little. As you can see, this value here is smaller than this one, okay? Precision of a double is 15. That's why it's much more preferable to use doubles in your code because floats are not precise at all. Okay, all of this works very simple. We just have to plug symbolic constants coming from limits.h and float.h. Easy peasy, ice cream vanilla. Now we have to compute ourselves these ranges. How can we do that? Let's start. So we're gonna do a file vim ranges int.c. So as usual, we include the standard input output, and that's it. So we call our main function int main, here we are. And then we start from the char data type. I want to represent signed, unsigned ranges of char. So let's start from char c max, okay. And we have c min is equal. Then we have unsigned char, of course, only c max unsigned is equal. Okay, so we do something like that. Now we understand how we can tackle this problem. Well, to solve this riddle, we can do in many ways. And if you watch the code of 10 different programmers, you get 10 different codes because basically programming is a crystallization of your ideas. So everyone has its own ideas. I think that a really neat approach for this kind of problem is to use bitwise operations. Let me explain better what I'm going to do here. We know that a char is composed of 8 bits, right? In C, we can write directly the values of our variables in binary. And this is pretty cool. For example, I can say C is equal to 0b. You write in this fashion, and then you write the binary. For example, if I want to write the letter A, I do 0, 1, 0, and then I do 0, 0, 0, 0, 1. Okay? This is the letter A, uppercase A in binary. If I really want to be super pedantic and write stuff in an hackerish way that nobody understands, you write directly in binary. Now, the cool part is that it's fairly simple to write the max value and the min value with the binary. For example, I know that the minimum value is always 1 and all zeros, right? So 1, 0, 0, 0, 0, 0, 0, 0 in a choose complement machine. So this is the min value because this is the bit representing the most negative value, namely minus 128. On the contrary, maximum value has 0 here and all ones. So 3, 1, 2, 3, 4. So this is the max value representable by a char. I can, if I want, to directly hard code this inside my Cmax and Cmin, but let's try something more more elegant. So what can I do? First of all, I don't want to write all these zeros and ones. So I do something like that. I use 0. So 0 literal. This is a 0 literal. Basically, it is an integer, so 32 bits, which are 0, okay? It's like writing like that 32 times, which is super tedious, right? So I write directly 0. Then what do? I use this bitwise operator, which is tilde. Tilde basically is going to invert all the zeros into ones and vice versa, okay? If they are ones, they become 0. So before here I had all zeros, 32 zeros. Now, after the tilde operation, I have all ones, okay? Easy peasy. Now, given all these ones that I have here, I want to perform shift operation. With this shift operation, basically, I want to bring, at this level, I want to bring here, you see, exactly at this level here, a 0, okay? So I want to transform to a 0. How can I do that? Well, I can do that with the shift operator, which is this one, shift 1. So the shift operator simply is moving all the bits one position to the right. Now, there is one problem here, that the shift operator maintains the sign of the value. And as you can see, this is negative. So in my case, if I shift, everyone here is gonna shift, but here I won't have a 0 as I want, but I'm gonna have another 1. Here, if you want to understand this point, just search logical shift versus arithmetic shift. So what do? First of all, I'm gonna cast this big binary into an unsigned. And an unsigned what? Well, an unsigned char, because I want only 8 bits. So what is going to happen when I do this cast? Well, here, many ones are gonna be deleted. So we have a truncation, 1, 2, 3, 4, 5, 6, 7, 8. So I remain with 8 ones, but this time, these ones are unsigned, okay? So when I perform the shift operation, I don't have the one that is maintained, I don't have the sign that is maintained, but I have this. I have all the values that are gonna shift one position to the right, and here I have a 0, okay? So this is what is going to happen, you see? Thanks to the fact that this value now is an unsigned char, okay? So I can delete this shift. Now I have this 0, 1, 1, 1, 1, 1. So do you recognize this value? Yeah, of course you do. This is the binary configuration of the char max, okay? So let's try what I just told you. Tilde 0. So here I have 32 ones. So let's write here so it's going to be easy to follow. Because these are operations, low-level operations that you don't do on a daily basis, of course. So 1, I have a literal 0, which is underneath the hood, a 0b, and 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, this big boy here, a literal 0. Then what do? I perform a tilde on 0, the literal 0. So what is going to happen, my friend? You know very well. All these zeros are going to become a 1. So we are going to write all these ones. Step 3, I'm going to say, okay, I want this, but when I perform the shift operation, I don't want to have problems with the sign of this boy. So every time you have a shift operation, just do it with unsigned values. So I'm going to cast this value into what? Into an unsigned char, okay? Unsigned char. So type cast to avoid matic shift, okay? So what is going to happen? I have 0b, 1, 2, 3, 4, 1, 2, 3, 4. Okay, that's the result after the typecast result. All right, so I have this unsigned 8-bit value. Now I just do a shift operation on this value. So I do this, right shift 1. The result is going to be this one, 0b, 0, 1, 1, 1, 1, 1, 1, 1. Okay, and then 5. I'm going to say C max is equal to the value itself. That's what is going to happen. So let's write this algorithm in code. So tilde 0. Now I have to typecast this to an unsigned char. So I can perform my shift 1. Okay, let's close this in round braces. So pay attention here to the precedence. We have the unary operation here to 0. That's going to perform first. Then we have the cast second. And then we have the shift third. The order here is important. So now I have this value, right? After this expression. And that's it. Allegedly, right? So let's do cmin and cmax, and then we're going to try to printf this. So cmin, what is the cmin? Char min is 0b 1 0 0 0 0 0 0 0. Okay, so how do I get that? Well, I can have, for example, 1, okay, and I want to shift this one. I want to shift that 7 position, which is, if you want to make the code more readable, we can say, including the limits.h, we can say here 1 shift char bits. Basically here I have the number of bits which are inside 1 byte, 1 char, per size of char, okay? If you want to be extremely pedantic, minus 1. So this big expression is going to resolve in 7. We can write directly 7, but this is the correct way to do if you want. Char bits, so it's going to be 8 per 1 minus 1. So I'm going to shift 7 position this one. I recall to you that this 1 underneath the hood is just one integer of 32 bits with a 1. If I shift this 7 position, I will get 3 bytes, which are 0. I can write here in hexadecimals, so it's going to be like 0x00, the first byte, 00, second byte, then again 00, third byte, and then I have 80. Of course, this is going to be on a little Indian machine, 80000000. So this 80, what is going to be? Well, in binary, it's going to be 1000. As you can see here, we have the 8 and then other 4 zeros, 04. All right. This is 80 in hexadecimal, okay? Okay, let's cancel this. And then cmax unsigned, we can simply do it like that. We do tilde 0. That's it. I'm gonna invert all the bits. Let's try to watch what is going on. So I'm gonna print the value of cmax is %d new line cmax. I'm gonna yank this line past, and here I put cmin, and here I put cmax unsigned, and cmin. Let's try to compile and launch. I forgot to put the semicolon here, exactly here. So I go on the line and I click the dollar to go at the bottom, and then I put the semicolon. Okay, let's go back. Compile. Here's telling me implicit conversion from int to char. That's no problem because I know what I'm doing. And as you can see, it works, right? The value of char max is 127. The value of char min is minus 128. So working with bits, we get this. Okay, here to remove this warning, I just do a char here. Okay, let's recompile it. Let's launch. And you can see it works perfectly. Okay, so that's the overall idea, doing these operations with bits. Okay, what do you think? It's understandable or not really? Of course, I repeat to you, you can calculate these values in a plethora of fashions. You can do loops, and when you get the overflow, you just understand that that was the maximum and so forth. I really think this is a neat way to find the value. Okay, let's watch the final product. So here we are. We have short and int and long. First of all, let's watch if it works. So I'm going to compile the code and launch. Okay, it seems that everything works correctly. Okay, for short, this time, as you can see, I've hard-coded in binary the value for short min. As you can see, I have 1, which is in the most significant position. And then here I have 1, 2, 3, 4, 5, 6, 7. And then, of course, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8 values, 8 bits, okay? So I have 16 bits, by which the first one, the most significant one, is 1, short min. Then what do? I just do tilde short min. I'm gonna just invert this. It's gonna become 0, 1, 1, 1, 1, 1. Okay. And then again, to get the max, I just invert the tilde. Then this is gonna cast it into an unsigned short. And for an integer, this time, what do? I do the same trick as before. As you can see, I do tilde 0. So I get 32 once. Then I cast it to an unsigned, so I can perform the shift without worrying about the sign. Then this result is going to be casted to an integer, you see? So I have the binary configuration here, which is 0 and all ones. So max int. I'm going to invert max int with this minus, as you can see here. So I get the inverse of max int. That's why I have to subtract -1 here. What a mouthful, right? But I think you can understand very well what is going on. then overall, the same ideas applies that you already understood. So I'm exploiting bitwise operations here. Shift operations at the end of the day are just multiplication and division, my friend. As you can see here, I have the number 9 divided by 8 is like making shift 3, okay? Right shift 3. If I take 9, right shift 3, I get 1. It's like division. If I make, on the contrary, left shift, I'm making multiplication. In this case, left shift 3 is like making the multiplication of a number per 8. Why per 8? Because it's 2 elevated to 3. I think it's fairly simple, right? These shift operations. Well, now the difficult part, my friend, because we have to manually calculate the float ranges. And to do that, we have to really understand what is going on with these real values. I always repeat on my videos that real numbers are qualitatively different from integer values because the way they're stored in memory. Indeed, we have this specific standard that regulates very precisely how a number is stored. We have a sign bit, like normal integers. Then, very differently, we have 8 bits, which are for the exponent value. And then we have the remaining bits, which are called the mantissa, which are the significant part. So we have a very specific way of encoding these values. I highly suggest you these 3 videos that I watched myself to understand better what is going on. And there's no point on me on repeating things that are already online. So I will leave you a link in the description to reach this guy. Amazing. If you don't understand really well floating point representation and you want to dig down, I consider these lessons the best. So hopefully you understand now what is going on, and we can implement your knowledge into actual code. So let's do vim range real.c. So we're gonna include stdio.h as always, and let's make a main float max. Then we declare float min. And then I'm gonna also use a mantissa. For that, I'm gonna use a double mantissa, so I can have much more precision. And now, to understand better what is going on, you can use float exposed. This is a marvelous website that allows you to really toggle single bits and understand better the floats. Okay, here I have a simple alf, which is a little data type to understand the principles. We're gonna use float. So here I have the sign bit. Here I have the exponent. And here I have the actual mantissa, namely the significant part. I'm going to make all zeros here. And all zeros, of course, is going to represent 0. Hopefully you know that some special configuration of the exponents are relegated for special values. So all the bits turned on are for infinity. If I have the negative, it's negative infinity, which is a special value that you can check by yourself what it means. Then here, if I have another bit turned on, whichever, I get this special value, which is not a value. So as you can see, this exponent, when as all the bits turned on, is gonna hide a specific value, which is not a float value. The same thing happens when we have all zeros here. When we have all zeros, we have the so-called denormalized value. Basically, every time I have a value here in the exponent, which is 1 or the maximum 254, right? Or this one, which is in this range, the max exponent that can be, I have a normalized value. Basically, it means that I have a 1, which is not written here. I have 1 point and the value, which is dictated by the significant part. So here I can have 1. This one is for the 1/2, 1/4, 1/8, 1/16, and you understand the point, right? So I have 1 point and that specific bit that represents the significant value. So play around with these ideas. And of course, the exponent is biased. So the bias for floats, it's 127. So what do we get here? If I turn all these bits on, right? All these bits. If I turn all these bits, I get 127, you see? These I get 255, which are for infinity. But if I get 127, I remove the bias. So 127 minus 127, what do I get? I get 0. So I have 2 raised to 0, which is 1. And here I have 1, right? Because I have the 1, which is not visible, 1 point, and this. What is going to happen if I turn this bit on? What do you think? This is 1/2. So I have 1.5 raised to 1. So I have 1.5 per 1, right? 2 to the 0. So I get 1.5. Cool. Here on the contrary, if I go to 128, so I do that, 128 minus the bias, which is 127, I get 2 elevated to 1, so I get 2. So 2 per 1 is equal to 2. What happens if I turn this bit on? 1.5 per 2, so 3. You see? So I suggest you to play with these websites to understand real well what is going on. Here you get the real operation. As you can see, right, you have the bias of 127, and this is the exponent that I have. So we have a sign, an exponent with a bias, and a significant part. The significant part is the mantissa, that 23 bits that you just saw. So every time basically you have 1, which is implicit when the exponent is different from 0, plus 1/2, 1/4, 1/8, 1/16, 1/32, and so forth. So we need a way to write this in code. So I can do a loop. I can say mantissa is equal to 1. This is implicit. And then I do for int I is equal to 0, I, no, not 0, but 1. I is minor equal than 23 and plus I. Okay. Then what do we do? I need the function power. So I'm going to include math.h, and we are going to use the power function. I have to say mantissa plus equal. In my float max, I want to turn on all these values, right? So I'm going to do plus 1/2. So 1/2 is 2 raised to minus 1. So here I hope you understand power or negatives. Otherwise, just watch a video on YouTube. It's super simple. So you do power of 2 to minus I. You see? So initially it's going to be 2 raised to minus 1, 2 raised minus 2, 2 raised minus 3, and so forth. Basically, I'm adding all these bits, you see? These, and so forth, till the last one, which is the one at position 23. So the mantissa essentially is going to get a value which is very, very close to 2, you see? It's going to be 1.9999999 something, okay? Never reaches the 2, because I'm going to add an half, a quarter, an eighth, and so forth, but it never reaches the 2. Okay, I have my mantissa ready. Then for the maximum exponent, what is the maximum exponent? Well, you understood before that when all the bits are turned on in our standard, we have infinity, or not a number, when some bits here are turned on, right? So when all the bits in the exponent are turned on, we have like a flag value, if you want. So the maximum exponent I can have is this one, is 1, 1, 1, 1, 1, 1, 1, and 0. Okay, so is 255 minus 1. The actual maximum exponent is 254. Of course, to this 254, we have to remove the bias, which is 127. So what do we do for float max? We do the power of 2 raised to 254 minus 127, okay, per the mantissa, you see? And I think we are almost ready. Let's try to launch this code and let's check if we are on the right path. So the max float is %f, new line, and we put fmax. Okay, we do the same for the symbolic one, so we can check. Of course, we have to include the file. So we're going to do that, include float.h. So here we're going to put float max. Here we are. Let's check it out. So compile, I'm going to compile range real, and then just launch. Boom. As you can see, it works. The values are totally the same. This is coming from the symbolic constant, and this is coming from my operation, which is the same, right? So you understand what is going on. I'm basically recreating with operations what is going on here, right? This for loop is like I'm basically turning on all these bits one by one, okay? And adding to 1, which is the implicit value of the mantissa, 1/2, 1/4, 1/8, and so forth, 23 times. So minor equal 23. So every time mantissa plus power of 2 elevated to minus I. Cool. Then for the actual exponent, I'm going to use 254, which is the maximum exponent. 255 is delegated for infinity and not numbers. And this is simply the bias, which is the value which is removed all the times, no matter what, to the exponent, to represent also really small values. So I have to multiply this coming from the exponent to the mantissa. And game is done. Of course, for the sign, it is specular. It is a specular value, only negative. This I can write in scientific notation, so it's going to be easier to see. So compile and launch. As you can see, it is the same. So this number elevated to 38. And we get this big boy here. Now, this is the max float that I can represent. Basically, I turn on all the bits in the exponent, but the last one. And then I just turn on bits here in the significant, in the mantissa. So we get 34028 elevated to 38, which is this one, right? 34028, 23 elevated to 38. Cool. Now, how about the minus value? Here we have two minuses to take into consideration. We have the normalized minus and unnormalized minus. So when all the bits here are turned off, we have a denormalized value. This can be considered as well as all the bits turned on, like another flag. So here I'm gonna have 1 this time, and here I have to remove all the bits. So this is the minimum normalized value. Now we're gonna make a program ourselves to compute this value, okay? Which is gonna be pretty straightforward. As you can see, this is very, very little. So we're gonna refresh the mantissa. What do we do now? F min is equal to what? Well, is equal to power of 2 to 1, which is the minimum exponent I can use, minus the bias. So 127, okay? I just write in this fashion so it's super clear what I'm doing. Per what value? Well, per the mantissa, which is 1. So we're gonna just do like before, we're gonna print the value and check if we are correct. So printf, the min float is %f, float min, yank past float, and we are gonna use the symbolic constant to make a double check, float min. Okay, let's try. So let's compile and launch. And of course, the number is so little that I need many zeros. Let's do 0.100. So this is gonna show me 100 elements after the point. So let's compile and launch again. As you can see, it seems like it is the same. Oh, it is the same, right? All the digits are equal. Perfect. Of course, we can watch in scientific notation to understand better, to visually grasp the value much better. That's why we use scientific notation with this kind of numbers, by the way. So as you can see, it's the same. Cool. So we understand how to compute max and min floats. Now, there is a value which is even smaller, which is the denormalized float. And basically, when the value is denormalized, the mantissa is equal to 0 this time. But not really, not quite. If I want to have the minimum representable number in floats, what is the trick? Well, to have a denormalized value, I have to turn all the bits to 0. Now, I don't have an implicit 1 here, but I have an implicit 0. So here I'm gonna take the smallest value possible, which is the last one. So this is 2 raised to minus 23. Let's do that. We're gonna do mantissa is equal to the power of 2 to minus 23. A very, very little number. So here we're gonna add float real min, and here I put float real min is equal to, we are gonna have as well this power, because this is the way the thing has been engineered, per mantissa as well, okay? So the same power, but this time the mantissa has only this tiny value. So let's copy again this boy, and we're gonna see this time. So float, so we have real min, and float true min is the symbolic constant. Okay, let's compile again and launch. As you can see, this is the value, and this is equal in both cases. And the value is smaller, right? Because it is raised to a bigger value, negative bigger value. Okay, my friend, this is the way by which we can calculate the value of a float. Of course, for a double, the thing is specular, so you don't really need any further explanation. Now I want to show you another trick, which is pretty cool. Now I want to explain to you this trick, but you have to understand unions. I never use them, but sometimes they can be pretty useful. So unions are kind of structs. Basically, the syntax is very similar. Indeed, all the variables inside an union share the same memory. Kind of strange, right? As you can see in my example here, I have an union that contains an unsigned int and a float. And both share the same space. Both share the same 4 bytes. Strange, right? What is going on here? So it simply means that if I assign a value to a float, a value is going to be assigned also to unb and vice versa. So it's kind of a strange data structure if you think about that. But it allows us to do very cool tricks. Now, if you want to understand better unions, I suggest you this video, as always, from Code Vault. Dude, pay me. I'm sponsoring your channel like hell. So, but it's very good. So it really deserves all the sponsors possible. Thank you, bro. You're amazing. So I assume now that you understand pretty well what is an union. And with this data structure, we can do something which is called type punning. So type punning is way to typecast without typecasting a value. So just focus on this image. As you can see, I have assigned a binary value to my nb, which is an unsigned int. So I do pf.nb. I'm accessing a member variable like I would do with structs and assign this binary value. I can do that with integers, right? I cannot do that with floats. So I assign this value, which is 42. As a side effect, even the float has this value. So the binary configuration of the float is going to be this one. If you understand the point that we can exploit here, we can refinedly, surgically control the binary configuration of floats. We cannot do that assigning the value directly on binary. So basically, I have a way to control all these bits like in this website, right? You can simply say, yeah, okay, you go on, you go on, you go on, you go on, you go off, and so forth. Because we have a way in C to write directly in binary with integers. So we can, in an hackerish way, control the binary configuration of floats. So long story short, this is a stupid example. I created this union. As you can see, the syntax is pretty straightforward. It's almost like a struct. So I have a typedef. So all my object unions are going to have this name. Like in this case, I declare a punning float that I call pf for punning float. I have an unsigned int, like in the example, and a float. Both have 4 bytes, so they both have the same space in memory, exactly the same. Now, what do? Let's do this together. I'm going to cancel this binary configuration, and let's say that I want this float to be the maximum possible configuration of a float, okay? So here I'm accessing the float binary configuration thanks to the nb unsigned variable, okay? So I know the first bit is for the sign, so it's going to be 0. Let's make it a little bigger. So it's going to be a positive max. Then I have 8 bits, which are for the exponent. You know that when all the bits are turned on, this is a special case for infinity. So I'm telling when all these bits are going to be on, I have infinity or not a number. Now I have not a number because here I have in the mantissa 1 bit turned on. In other cases, I have infinity here or minus infinity. So the maximum exponent I can have is 7 bits turned on, 1, 2, 3, 4, 5, 6, 7, and a 0, okay? Then I just need 23 ones, right? Because this is the maximum value I want to represent with floats. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3. Boom. Here we have the binary configuration of the biggest float. Let's check it out if it works. Here I have the printf maxis, and I access, you see the trick here, you see the hackish part, I access the float. So I give the value to my unsigned int, which is this one. So this memory is going to be arranged, all the bits are going to be arranged in this fashion, I can do that. But in my printf, I'm accessing the float. Let's check it out if it works. So gcc float punning, let's go to launch. As you can see, the value is the same, right, my friend? Because we are tweaking the binaries. Thanks to this special punning technique, I think you have a good panoramical understanding of the many ways you can calculate the value. Here it's super cool because you can finally control the binary configuration of floats and doubles as well. We are not wasting our times with doubles because it's just a bigger data type, but the principle starts the same. So of course, I will leave many links in the description so you can go as down as you want in this rabbit hole, but essentially that's it for this video. I've made also this little program that allows you to write the binary configuration of all the floating point numbers. So you have this little algorithm. Indeed, I found this piece of code online. So look how cool is this code. You just plug in a value and it's gonna show you the binary configuration, right? I think it's pretty cool. For example, 1.0, of course we know is this one because we have 127 minus 127, so 2 to the 0, 1 per 1. If I do, for example, 2.0, of course we have a 1 here because we have 2 elevated 1 and so forth. You understand this point. Of course, I will push everything on GitHub so you can check by yourself. Hopefully I managed to explain you something interesting, and see you on the next one. Thank you, my friend.